All right, let's dive in. Today, we're going to plug into the secret world of alternating current, AC. We're going to see how just three little components can team up to pull one clear signal out of a whole lot of noise. And trust me, this is the magic behind everything from your car radio to your Wi-Fi.
So, let's start with something you've probably done 1,000 times. You're in the car, you're turning that radio dial, and somehow, out of all that static, all those different stations floating through the air, you lock on to just one. How in the world does your radio do that? How does it know which signal to grab and which ones to just, ignore? Well, the answer is some seriously cool physics, and that's exactly what we're going to break down.
Okay, so before we can even get to the radio tuning part, we've got to get the basics down. There are two fundamental types of electricity, two different ways it gets delivered. You can kind of think of them as two different languages, and circuits have to be designed to understand one or the other.
So, on one hand, you've got direct current, or DC. This one's easy. It's like a one-way street. The electricity flows steady in just one direction, just like the power coming out of a battery. But then you have alternating current, AC. This is what's coming out of your wall sockets, and it's totally different. The electricity is constantly flipping direction, back and forth, in this nice, smooth wave.
So you might be thinking, why do we use this wacky back and forth AC stuff for our power grid? And the answer is actually really simple. It's just better for the job. It's way more efficient and cheaper to send AC power over super long distances, from the power plant to your house. That's actually why it famously won the war of the currents back in the day.
All right, let's start building our circuit. We're going to start with the simplest component of all. Think of this as player number one in our little game, the resistor.
Now, a resistor is super straightforward. What you see is what you get. In an AC circuit, when the voltage wave goes up, the current wave goes up right alongside it. When the voltage drops, the current drops too. They're perfectly in sync, moving in perfect lockstep. No drama, no delays. And that really gets to the core of what a resistor does. It's just pure opposition. It's like electrical friction. Its only job is to make it a little harder for the current to flow, so it cuts down the amount of current, but, and this is key, it doesn't mess with the timing at all. Voltage and current stay perfectly in sync.
Okay, resistors are simple enough, but now is when things get really, really interesting. Let's bring in two new players that are total game changers. They're going to fundamentally mess with the timing of our AC circuit. Say hello to the inductor and the capacitor.
First up, the inductor. The best way to think about an inductor is that it has a kind of electrical inertia. It hates change. It fights against any change in the current. So when the AC voltage gives a push, the current is, it's a bit lazy. It's slow to get going. The result? The current wave ends up lagging behind the voltage wave, and not just by a little bit, by a perfect 90 degrees. So the voltage leads, and the current is always playing catch-up.
And here's the crucial part. An inductor's opposition isn't a fixed number like a resistor's. It's called inductive reactance, and it actually depends on the frequency of the AC. Think about it. The faster the current tries to flip back and forth, in other words, the higher the frequency, the harder that inductor is going to push back. It fights change, remember?
Okay, next up is the capacitor. And you guessed it, it does the exact opposite of the inductor. Instead of opposing changes in current, a capacitor opposes changes in voltage. So what does that mean? It means the current actually rushes in first, charging up the capacitor's plates, and only then does the voltage build up. The current gets a head start. So in this case, the current leads the voltage, again by a perfect 90 degrees.
And just like the inductor, its opposition, called capacitive reactance, also depends on the frequency. But you guessed it, it's the other way around. Capacitors have a really tough time with low frequencies. They basically block them. But high frequencies, they let them pass right on through. No problem.
So let's just sum this up, because it's the whole point. The inductor makes the current late to the party. The capacitor makes the current show up early. They are perfect opposites when it comes to timing. So, we've met all our players, the steady resistor, the lagging inductor, and the leading capacitor. Now for the main event. What happens when we put them all on the same team, in one single circuit? This is where the magic really starts.
Okay, picture this. You've got the inductor pulling the current back, trying to make it late. At the same time, you've got the capacitor pushing the current forward, trying to make it early. It's a perfect tug of war over the timing of the current. So, what happens if we find that one perfect frequency where their push and pull are exactly equal? What happens when they completely cancel each other out?
The answer has a name, and it's an incredibly powerful idea in physics: resonance. This is the whole secret. right here. For any combination of an inductor and a capacitor, there is one single special frequency where their opposing forces perfectly balance out. We call this the resonant frequency. And at that exact frequency, it's like their time-shifting powers just disappear.
So, if the inductor and capacitor have canceled each other out, what's left to stop the current? Just our good old friend, the simple resistor. That's it. This means the total opposition of the circuit, the fancy word for it is impedance, suddenly drops to the lowest it can possibly be.
And we all know what happens when opposition is at its lowest, right? The current that can flow through the circuit becomes absolutely maximum. You get this huge surge of current. But, and here's the kicker, it only happens at that one specific resonant frequency.
This is so cool. The circuit basically becomes a super selective filter. It's why we sometimes call it an acceptor circuit. It accepts that one special frequency by letting a massive current flow, and it pretty much rejects or ignores everything else.
And now we can finally answer our question from the beginning. That sharp peak of current, that is your radio station. When you turn the tuning knob on an old radio, what you're actually doing is changing the capacitor inside. You're changing the C in your LCR circuit. So think about it. Every radio station is broadcasting at its own unique frequency, right? Your car antenna is getting hit with all of them at the same time. But when you turn that dial, you're changing your circuit's resonant frequency. You're tuning it. And when you adjust it just right so that its special resonant frequency matches the frequency of the station you want to hear, bam, the current for that signal and only that signal spikes through the roof. It gets amplified, and that's what you hear loud and clear. Everything else just stays as quiet background noise.
And you know, this whole idea is so much bigger than just radios. This principle of resonance, it's the absolute foundation of all modern wireless communication. It's how your phone picks one cell tower, how your Wi-Fi router talks to your laptop, how your GPS locks onto a satellite. It's all about tuning a circuit to select one specific conversation out of an endless sea of noise. It really makes you wonder, doesn't it? What other signals are flying through the air all around us right now, just waiting for us to build the right circuit to listen in?